This content is brought to you by BEC Financial Technologies, developing and operating IT for Danish banks.
For the next presentation, as you can see on this stage, we are joined by Marcin Iwanowski, Microsoft MVP in the Azure Patterns and Practices category. But I would also say that an absolute MVP in training people to excel in their career. If you don't know this man by any chance, this means you might have not been very active in excelling your skills, because he is a very well-known trainer in the Microsoft world. Also a co-owner of BIMBEARS, who provides experts to Western IT markets, consultant at SoftwareONE AG, previously developer, team leader, project manager, head of departments in organizations of various sizes, from a dozen to over 100,000 employees. Active trainer, as I said, collaborating with the largest educational centers in Poland. Today, presenting the topic of Introduction to Quantum Programming with Azure Quantum and Microsoft Q#. Marcin Iwanowski, please give him a warm welcome.
Thank you. Let me quickly switch. Okay, welcome everybody today on my presentation about quantum computing, actually more about Azure Quantum. So today, from developer perspective, I would like you to introduce quantum computing and Azure Quantum, and let's answer the question if the quantum computing is something that we need to focus on right now, or maybe we can wait a moment, right? So just from developer perspective, let's check that. As I was introduced, I am co-owner of some company from Podlasie, BIMBEARS, where we specialize on Microsoft technologies. Currently, mostly I'm in one of our clients, acting as an Azure architect. I'm also an MVP, some trainer, etc. But yeah. Okay, let's quickly answer the question why we are talking about quantum computing at all, right? Why it is important, why it is trendy. But before I can do that, I need to just go back a little bit to 2009. There is just the date there. What was in 2009? In 2009, I had also a presentation where I was talking about some parallel programming, right, in .NET, doesn't matter, right? But basically in 2009, computers with multi-cores, for example, with 100 cores or something, was nothing new, actually. Maybe it was not like that I had the laptop with many cores. And in 2009, we were talking that in a few years, actually in 2015, most of the desktop computers, most of the personal computers will have multiple cores. And what happened actually until today, right? Until today, so until 2025. Actually, yeah, it's true. I have a desktop computer that has 32 logical cores, right? Even I can buy 100-something multi-core processor if I can afford the price, right? But it's possible. Also, I don't know if you know that there is some Azure service called Azure Dedicated Host, and there you can also rent some multi-core server, right, by spending only more than 40,000 US dollars per month, right? So basically we see maybe not evolution, not revolution between 2009 and 2025, but still we see some just evolution, right? It's just evolution, right? But if you are talking about the problems that we have and what we had even before, the problems still are the same. So, for example, let's take one of the simplest problems. Okay, maybe not simple one. But if you would like to create a path, create a trace between the shortest one, between all the points that you have, right? Then it's not an easy task. Of course, we have many algorithms that can do that, that can bring us some answers, but usually those algorithms doesn't bring us the best answer, right? Of course, the problem depends of how much data we have, how many points we need to follow, let's say, right? Another problem, here we have ship containers, right? How to put containers to the ship so the weight of it is balanced, right? It's also not so easy problem. Actual algorithms are simple, but we don't have enough computer power to solve it in basically our lifetime. Yeah? And so on, we have much more such problems. Basically, here I'm talking about exponential complexity, exponential problems, right? To visualize you how such problems are very fast becoming very hard problems, let's make an experiment, right? If I have a paper that is just 0.1 millimeter thick and I will fold it, right? Then I will have 0.2, right? If I will fold it once again, then how much we will have? 0.4. If I will fold it only 42 times, how do you think the thickness it will be? Just guess. Okay, we don't have enough time to calculate it, but basically it will be more than distance from Earth to the moon, right? Actually, it will be more than 400,000 kilometers. Just remember that we started with millimeters, right? So this is how those exponential problems, how quickly those exponential problems becomes really hard, right? Okay. And such problems in our daily life, we have many such problems in our daily life, for example, whole security, cryptography, algorithms, etc. Are using that. For example, if we would like to invent a new material, then also we have such problems. If we want to if we want to have a new medicine, right? It's not so hard to make a simulator of the human, right? But it's very hard to check how anything, if we put inside the human, will behave, or how human will behave, because we have so many data to calculate, right? And also AI, machine learning algorithms, also we don't use the best algorithms that people have, basically, right? Because we don't have so much power to use them, right? Okay, so now let's talk why quantum computing can solve such problems, right? Why we are talking about quantum computing here. To do that, I need to introduce you some basic of quantum computing, right? So there will be a little bit math, but just a little bit, right? Just a little bit. But let's start with something that you understand. In the classical computing, we have bits, right? We have 0 and 1. I think that everybody understands that. And bits can be combined, right? So we have more complex numbers, etc. So actually, in the quantum world, we have similar thing. We have qubits. It's just the bit, but in the quantum world. This qubit also can have 0 on 1 state. And also, these qubits can be combined to more complex number, okay? And that's all what you already know. Everything further, I will say, will be something new, right? So 0 and 1, it's not only those states are not only the possible states that we have in the quantum world. Actually, the qubit can be in the superposition state. What does it mean, the superposition? The superposition means that we basically don't know what state of the qubit is, but don't know it's not a right word. Actually, he is in all the states all the time, right? And before we will not watch it, so as soon as we will watch on which state it is, for example, we will observe that this qubit is in zero state, then if we will be watching once again, then always then it will be zero, right? So it's like USB port in my laptop, right? If I'm trying to put some USB stick to the port and doesn't fit, so I flip it, right? Trying once again, doesn't fit, right? You feel that? I'm flipping once again, doesn't fit. Before I don't look here, I don't know in which state the USB is, right? So once I see that, then I know that this particular qubit is in that state, right? And let's do a little bit math. Actually, we can, this is the equation that can present the quantum state. So the quantum state can be presented by those two numbers, alpha and beta. So this is like probability of having zero state and probability of having one state, right? But basically probability is very wrong word here, but we don't have the better word, right? But everything that we will calculate, we'll be using some maths that is based on probabilities, but it's very wrong word here. Yep. And actually this alpha and beta needs to equal 1. Actually, it's logic, right? Because alpha is some probability, beta is some, then we don't want to have more than 1, right? Than 100%, for example. Okay, but why scientists put square here, right? Now a little bit more math, right? So, if there is a problem that scientists cannot explain, then he take additional dimension to the equation. So with additional dimension, usually they can solve more problems, right? So actually, alpha and beta are complex numbers, right? But this is just information for you that alpha and beta is something more, right? I will not go more deep than that, right? We will stop here, right? But just remember that alpha and beta is something more. Okay, so let's take the qubit that is in ideal superposition state. So the ideal superposition state is that we have 50% chance that we will have zero state or one state. So how it will be represented by this equation? It will be like that, right? So if we will do square of this, then we will have half plus half equals 1, right? So yeah, this is the mathematical representation of ideal superposition. Superposition and basically the quantum state also can be represented in the Bloch sphere, but I will go further as we don't have enough time. Let's now focus on that. So if I have 2 qubits, right? Before we are talking just about 1. If we have 2 qubits, then basically we have 4 possible states, right? Because we can have 0, 0, 0, 1, 1, 0, and 1, 1, right? So 4 possible states. If we will add 1 more qubit to that, how many probabilities we will have? 8, right? If we will add 1 more qubit, just 1 more qubit to that, how many probabilities we will have? 16. Yeah? So you see, this shows you that by adding just 1 qubit, we are double the computing possibilities of our computer, right? Just by adding one qubit. So it's totally different than in the classical computing where we have transistors, etc. Okay? So what does it mean, basically? What does this qubit mean? Basically, qubits can be simulated also. So on the classical computer, we can simulate qubits. It's not a hard knowledge. Actually, we have some simulators. I will show you that later. So if we will try to compare the classical computer to the quantum computer, then, for example, on this machine, on this laptop, I can simulate up to 30-something qubits, right? It's 30-something. Okay? In 2019, we had quantum computers that have more than 50 qubits. In 2023, there was created Atom Computing, or its company name, Atom Computing, created a computer that had more than 1,000 qubits, right? But what does it mean 1,000 then, right? 1,000. Let's say how many qubits we need to break the RSA key that consists of 4,000 bits, right? It's you need to make it double and add something. So let's say that it's about 10,000 qubits, right? To break such key. In 2023, we had 1,000 qubits already, quantum computers with 1,000 qubits. Today we have more, a little bit more, but it's more important, during the last year, USA government announced that they will build, together with some companies, of course, they will build a quantum computer that's called Quantum that will have 1 million qubits. When? 2027, 2028. Very soon. Right? Even right now, I'm not in the position to show you a very good demo that you will say, wow, what a demo, right? Because I don't have access to such computers. But I think if I will do the same presentation next year, then I will have something to show you. We will be able to break some simple keys, for example, from the cryptography. Right? Okay. So on this part, I wanted to just show you why it's important to talk about the quantum computing, right? But I want to add one more thing, one more magic behavior of quantum computing. I want to add something that is called entanglement, right? Entanglement. In Polish, splątanie kwantowe. Entanglement. So what's that, right? So we can have two qubits, let's say 2 electrons, for example, but qubit doesn't have to be electron. Right? Let's say that we have 2 electrons, right? And we will put both of them in the superposition state, right? And we can make we have some instruction that we can run on them, and then both of them will be entanglement. What does it mean? It means that if I will send this one electron to another country, whatever, right? And somebody will check the state of this electron, of this qubit, then immediately, in the same moment, my qubit will have the opposite state, right? Scientist doesn't know how it works. There is no theory in the world that proves that it works, but there was a lot of experiments that basically shows that it works. For example, in 2017, in Science, there is an article that describes exactly that, right? One of the China laboratory built a satellite, and in the space, this satellite just was bombarding some atoms, right? And such, let's say, cutted atoms usually are in the entanglement state. And one of, let's say, electrons was sent, the satellite, one of the electrons was sending to laboratory in Austria. The second was sent into the China, right? Of course, there was 1 million of them sending here and sending there. And they proved that if something was watched in one of the laboratory, then immediately in the second laboratory, the let's say, counterpart of these electrons has the opposite state, right? So we have a much more proof that it works, but nobody knows how it works, actually, right? And quantum computers are using that thing also, and we can have fun with that. Okay, let's now talk about Microsoft, basically, and let's talk what Microsoft brings to that world for us. So I will divide it for 2 parts. Let's talk a little bit at first about the quantum computer that Microsoft is building, right? Maybe I will start here, because a few months ago, 2 months ago, I think, Microsoft announced that they created its first quantum processor. The size of it is about the hand, right? Something like that. And actually, it's only 8 qubits, so not so much power. But the more important is the architecture here, right? So now I will go back 1 slide, right? So basically, building a quantum computer, the simple one, it's not so complex. Many companies can do that. There is many techniques how we can do that. For example, we can build some trap for electrons. We can see if the photon will go one path or another, etc. There is a lot of many different techniques how we can build the quantum computer. But the the biggest issue with the most quantum computers is that the noise from around, basically from around the world, not only from the Earth, actually, right? So it's very complex if we have, for example, the superposition, to keep many qubits in the superposition for a long time, right? Because of this noise, right? That's why Microsoft started to build the computer in much different way. It's called topological quantum computing. It's just the architecture, how the quantum computers can be built. So basically, they are building logical qubits that consist of many physical qubits, right? And they are using some techniques to keep the state. You can read it on the site that I will go in a moment, right? Okay, so, and they achieved that basically this year, and for, I think, next few years, next 2 years, basically, they will build a much more powerful quantum computing using that architecture, right? So this is the first thing that Microsoft is working on. And the second thing that we already have access to from few years, I think, is the service on Azure. It's called Azure Quantum, right? And what gives us Azure Quantum? At first, it gives us the simulator, right? So if we want to play with some quantum language and check how our programs will behave, we can do that. But also it gives us the access to real quantum computers. Not yet to Microsoft One, but maybe in the near future, right? And we have basically 3 more. It's just, as you can see, let's say third-party vendors of quantum hardware. Also, what Azure Quantum, Microsoft gives us, they gives us the language. It's called Q#, right? So in Q# we can write the code. This code will be compiled to some intermediate representation, and this intermediate representation can be run on many different hardwares of the quantum computers. So actually it's something like .NET, right? .NET is also compiling to the intermediate language, and then it can be run on many different architectures like AMD, x86, etc., right? Okay. But yeah, let's see that, how it works. At first I will start, if I will connect to, okay, so let's start with that. Actually, at first I want to show you how the IBM quantum computing looks like, just because it has good representation here. So not only using the code, but also using those lines, you can build something, right? I want to press delete. Delete. No, I cannot. Okay, delete, okay, and delete that. Okay, so basically here you can see that we have 4 qubits, right? And now I can just take some instruction from here, put it to some qubit, and something will happen, right? Right now, and here you can see the probability. If I will not do anything with any qubits, then all of them are in the 0 state, right? And so this is why I will, at 100% probability, I will have the 0 state for all of them, right? Now let's put Hadamard gate. It's a superposition, right? So now I have probability that we will have 0 or 1 on the first qubit. And the probability is equal. So we have 50% of chance that on this qubit we will have 0 on 1, right? And then we can take another instruction. Here we have entanglement. Okay, let's see that. So we have the probability that we will have 0, 0 or 1, 1. But wait a moment. I told you that if 2 electrons or qubits are in the entanglement state, and when we will observe one, then second one will be the opposite, right? But here we see that or we have 2 zeros or we have 2 ones. It should be 1, 0 or 0, 1. Actually, programmers are lazy, so they just make a decision that if there is entanglement and we will watch the qubit, then the second one will have the same state. It's just, it's not the science, it's just how they see that in the programming language, right? Okay, and then later on we can do some other things, something more complex, for example, etc., etc. I don't want to explain you all of these instructions here, right? But you see that I'm changing basically the state of those qubits, okay? And of course, we can write the code, right? Here we have the code, how we can write it. And of course, I can run it on the real quantum computer, right? But actually, on the just weak computer, 100 qubits, it's not so, let's say, powerful, right? Of course, it's more than my laptop can simulate, right? But still, we need a little bit more to do things that will have wow effect. Right? Okay, I will not run it, because usually when I will press run, then we need to wait about 15 minutes, sometimes half an hour, something like that, right? So it's not the real-time execution. You know, there is a lot of geeks that want to play with that, right? Okay, now let's move to the Microsoft Word. So at first, really read this. If you go to the quantummicrosoft.com, you can read about the vision, about this Majorana processor, etc., etc. Really great articles here. But also you have here the quantum computing, let's say, samples or code. So we can write something. Here is one of the simplest and still useful programs that we can have. This is the program that just generates a real random bit, real one, because the classical computers doesn't have the real random numbers, right? And how to generate random bit? Let's make the Hadamard gate. Let's put the Hadamard gate on the qubit, so we will have superposition, right? And then let's watch it. That's all, right? And then let's measure it. This is measure, right? It's not watch, measure it, and then we will have something. We can run this program. This will be running, also, of course, right now on the simulator, and I can run it, for example, this amount of time. Let's run it 100 times, right? And we see here the results, right? So usually, 100 is not also a lot, but we see that really the Hadamard gate works here, right? That we have about 50% of getting the 0 or 1 state. And of course, here we have the copilot. We can just write the sentence, generate me the code that give me the qubit with the 75% probability, and it will do that. But I don't want to focus on that. And the next thing is that I want to show you is, let's start with this one, how we can use the Azure Quantum service on Azure, right? It's a very simple one. You need to just create a workspace that is called Quantum Workspace. Just find it here, create that, and that's all. And here we can see that I have 3 available providers, right, for quantum computers. And basically we can use them. How we can use them? Actually, we need, for example, Visual Studio Code. Then we need to write the code and run the code on one of these computers. And we have some quotas. So basically we have, let's say, 500 credits, whatever it means, right? Because those 500 credits are spent differently on different providers, actually. On one provider, we are counting how many seconds your program works. On a different one, how many qubits you are using, etc., right? But actually, 500 credits is not we can have a fun with that, basically. Yeah. Okay, let me go to Visual Studio Code, and let me demonstrate you one of the algorithms. Okay, in the Visual Studio Code, I can also I can write something in the Q#. I don't want also to explain you the details of Q#, but you see it's quite similar a little bit to C#, more maybe more to F#, right? We have some strange functions because, for example, we don't have the casting functions, right? Basically, we have the function, but we don't have the syntax in the language yet for casting, etc. But basically, most of those instructions are understandable. The one thing, of course, what we need to learn is those instructions, right? H, RY, RX, etc., etc. But as I said, we don't have so much time to explain all of them, right? But I would like to present you one of the algorithms that shows us that quantum computer can be better than the classical one, right? It will be not simple problem to understand, and even worse to understand the solution, right? But let's try with that, and I will leave you the book where you can read why the quantum computer is better. But we will do the simulation, and we will see that really it works better. So it's a CHSH game, right? So it's a game where Alice and Bob participate, right? So Alice and Bob got some bit. Alice got X bit, Bob gets bit Y, right? Y. And they cannot speak each other. Alice and Bob cannot communicate at all. right? And they need to output some bit also. So based on that X, Alice needs to answer something. So if I have 0, I can answer 1, or whatever strategy they want to he wants to take, or she wants to take, or he wants to take. Right? So when they win, now the question is, when they win the game, right? They both are playing, and the goal is that they both will win or they both will lose, right? So when they win when the AND operation of the X and Y that they got is equal the XOR operation of what they answered, right? So let's look here, right? If Alice got 0 and Bob got 0, then the left hand of side of this equation will be equal 0, right? Basically, usually it will be equal 0. There is only one case when the left hand side of this equation will be 1, right? Okay? So Alice and Bob knows about that, right? Basically, right? And before they started the game, they started to think how we can win, yeah? How strategy we can take to make, I don't want to say how many wins, because it's a question to you, right? If you understand the problem, if you are the Alice and Bob, what strategy you will take to have maximum of wins, right? So if we will, let's say, play 100 times, right? So what strategy you will take to have the maximum number of wins, right? Look at that. For example, always choose 0, exactly, right? So if Alice will return 0 and Bob will return the 0, then right-hand side will be 0, right? So if the right-hand side will be 0, then we have how many chances that we win? 75% that we will win, right? And of course, the second best strategy is that always return 1. So whatever comes to me, here or here, always return 1. And then also we will win 75% of chance of games, right? But in the quantum world, we can have better strategy, right? Actually, this is the best strategy that we can have in the classical world. In the quantum world, we can have better strategy. And this is how I would like you to show you. So let me explain quickly how this code looks like. I will play 10,000 times, right? 10,000 times. Then I will generate random bits, X and Y. And then Alice and Bob will play. In the classical way, the strategy here is simple. Return always false, right? Return always 0. And then I do the calculation, left-hand side, right-hand side, and I'm checking how many times I won. And in the classical world, you see that usually, you don't see. Sorry, you don't see. Where is my presentation? Just exit. Sorry. Okay. Now you will understand what I'm doing. So I will be playing 10,000 times, right? And I will generate X and Y for Alice and Bob, right? Random numbers, and then we will play. Alice and Bob will play, but play for the classical way, the play strategy is very simple, right? Always return false and false. And then I'm calculating the left-hand side, right-hand side, right? And I'm calculating how many times I won. So usually it will be around 75%, 75%, right? Okay, if I want to run it on the quantum computer, I can choose my quantum workspace that I created on Azure, and I'm just choosing the provider. I'm just clicking play here, and that's all. And it will go to the quantum computer, and in some time, sometimes 5 minutes, sometimes 2 hours, right? We will have a result. Result is just a JSON, right? It's just the JSON with the with our results. Okay, and now I will show you the quantum way, right? So here I have the same. So here is the classical way. Here will be the quantum way. In the quantum way, this is this part only changes, right? So I'm playing the game with the quantum strategy. I don't want to explain in detail this algorithm, but looks quite simple, right? But it's not so simple to understand. But 2 more hours and you will understand. But let's check how it looks like, right? Let's check how it looks like. Yeah. How many wins you see? 85%, right? Here. Yeah. We don't have enough time to explain actually how it works. Because it's based on the measures that we can do with the entanglement qubits, right? But there is a mathematical proof, even mathematical proof that if we are doing some operations, then our chance will be slightly better than in the classical way. Maybe not even slightly. The 10% chance of wins, it's really a change. Right? If you want to understand that, I recommend you a book, right? Introducing Microsoft Quantum Computing for developers. I spent some time chatting with this guy, really cool guy, and he has a lot of thoughts about that thing, so I recommend you that. Right? He explains the details of the language, he explains the details of some basic algorithm, etc. So really it's a good start for developers, basically, if you want to read it from that perspective. Right? And basically, if you want to take a picture, go on. Yeah. If you want to take a picture, go on. Yeah. And basically, that's all from my side. So during that short presentation, I wanted to explain or answer the question if the quantum computing is something that we need to start learn or teach on the other side, right? And basically, yes, I think so that every of us should have the awareness of what quantum computing can change in very near future, right? I think in 2-3 years, right? Of course, it will be not like that we'll be inventing some algorithms, some quantum algorithms, because really we need to cooperate with scientists to invent some quantum algorithms. It's very tough knowledge. But we will have ready-to-go libraries, right? With some algorithms to solve some problems, and that's how we will be using the quantum computers. Right? And I show you also what Microsoft is doing in that world. So on the one hand of side here, they are building the quantum computing in a different way than other players are doing. And of course, we have a Azure Quantum service where we can even today start to play with that. Right? And that's all from my side. If you have any questions, feel free. Yeah.
So, do we have any questions? Yeah.
Thank you for your presentation, Marcin. So maybe you have any ideas, like a vision or something, about how exact will quantum computing will be useful in the nearest future? Because the examples that we just saw, it's more or less like theoretical things. And for me personally, I don't know any kind of examples how quantum computing really can help any kind of business, people. Anyway, just any thoughts. Thank you.
So let's take the easiest example, right? if you have, for example, 100 points in the Poland that you want to visit, right? And you want to have just find the shortest way how to do that, then you will use the ready-to-go quantum library that will be prepared to that time with some algorithm, right? And you will just upload the points there, you will run the code there, and then you will get back the answer to what is the shortest way. This is one of the examples, for example, right? But it's a very, very basic example, right? But now we can think about drug developments, etc., where we have much more data, right, than 1,000 points, right? And then we'll be uploading those data to the quantum computer, and this quantum computer will be just calculating something. That's all, right? But in the fast way, right?
Marcin, great presentation. What inspired you to look into the quantum computing? Was it a challenge that you were facing with, or I cannot believe that it must have been.
Tell you.
It was the tracing the optimal route, right?
You never guess what inspired me. Actually, AI inspired me, but not in the way that you think about, because everybody talks about AI today, right? But I think really this will be the revolution, right? Not the AI. And yeah, exactly. Yeah. Basically, I don't want to talk about things that everybody is talking. That's why I'm trying to find some other topics.
Do we have any questions in the room? I don't see any hands, so maybe the sneak peek of ideas sparked some business ideas for you guys about this topic. Maybe we can talk about that during the coffee break, which approaches us, but also approaching us is Paweł right now, to present our speaker with an award. Yeah, a small gift bag and an award. So please, a round of applause for our speaker. Thank you so much for your presentation.